Everybody. So welcome to the late night show. So episode 2, we are going to talk about probabilistic modeling and density estimation. So one quick update. I mean, yesterday you had the tutorial, right? And with a heavy heart, I should say that it did not get recorded. So sorry about that, but it didn't get recorded. Sorry, it was again an issue. So so let me just start with this lecture. So what we want to do today. So take this. Close, or maybe I take it here. Actually, that's gonna. Oh no! Come on. Okay. Okay, so let me just start quickly with that. So last time we talked about the basics of machine learning, right? So we wanted to know what is machine learning in general and what are we supposed to do there. So we said like we had this kind of, mild definition that machine learning is basically a set of data-driven approaches that they are helping us to understand the environment and the behavior. And these set of approach is going to help us to not only understand how the environment behaves, but also be able to somehow develop a kind of understanding which generalizes. So we talked about this, that any machine learning problem or any machine learning task is being done through 3 major steps or 3 major components. One of them was the data set. So we collect data and then we specify a model which is capturing the pattern inside the data. So we talked about this example of the Ohm's law, where you see that the current and voltage have a proportional behavior, and then you try to model it, a linear model maybe. You don't know whether this is the perfect model or not, but it's capturing the pattern. The one increases, the other one increases too. And then you try to develop a learning algorithm. And the learning algorithm, basically what it does is that it's taking the data set and tries to just somehow make that model in a form that it generalizes in future. So we talked about one particular problem, which was the problem of clustering, right? So what was the problem? We had a bunch of data points. These data points in general are in, say, d-dimensional space. And these points are given to you out of some data collection, right? And what you wanted to do, you want to put them into clusters. But this cluster is not supposed to only operate on your data set, but it's to be able, if I give you a new point, you tell me what the cluster is, right? So this was the idea, the problem. And what kind of problem is it? Was it supervised or unsupervised? What was it? Unsupervised, right? Why is this unsupervised? There is no label, exactly. So when you see a point, there is no reason that, there is no ground truth about the fact that this belongs to one cluster. Clustering is basically a pattern you're doing by your own, yeah? So this was the idea of unsupervised learning, and then we talked about the model. So we had this particular model which was thinking about particular, centroids, and then you consider k different centroids. Any point is within one cluster when it is close to the centroid, right? And what was the learning algorithm we developed last time? What was the algorithm? K means clustering, right? So the algorithm was K means clustering. We said is a good clustering algorithm, right? So this was the algorithm. It had 2 major steps. One of them was cluster assignment. So it looks at every single point inside your data set, sees what is the closest centroid. This is going to be the cluster, right? So you choose the clusters, then you just update your centroids, just go in the center of the points you have in each cluster set, and then you repeat this. You keep on repeating till nothing is changing. And once this is the case, then you say the algorithm is converging. So is this algorithm necessarily the optimal algorithm you can use for clustering? We talked about this? No, this is not the optimal. But what do we mean by the optimal? Did we have any sort of metric that we can define being optimal in the sense of clustering? That was the risk, right? So we said, like, you go ahead, say you have a bunch of data points, right? And say you have done the clustering with this k-means clustering. At the end of the day, you can just find the distance between each point to its centroid, right? And then if you sum up all of these distances and average them out, this was what we called it the risk, and we wanted to make this risk minimized, correct? So this was the idea. K-means clustering could not do it perfectly because this was essentially a hard problem to solve, so it was doing it iteratively, right? And then this was the idea, so we talked about this, and now what I want to do today, I want to open up a new unsupervised learning problem, which not only is a new one, but it also helps you to get a bit of understanding about why we did all of those things inside k-means clustering. And the problem that I want to talk about today is the problem of density estimation or distribution learning. So what do I mean by that? We're going to hopefully get clear at the end of today, but let me just give you a quick agenda about what we're going to do. So first, we are going to have a bit of review on probability theory. I just want to make sure we're all on the same page. And then after that, we're going to talk about the idea of maximum likelihood estimation. So if we have a random process and we want to model it and we'll find out what is the distribution behind the scene, the best approach we can do, again in some specific sense, is maximum likelihood. And we're going to focus on one, say, easy form of maximum likelihood when we think of everything being Gaussian. And we just talk about this, then hopefully you can extend all the idea to other things as well. And we are then going to get back to the clustering problem. We're going to see that what we did actually in clustering with k-means clustering was a sort of same thing. So we were thinking of a sort of collection of Gaussian distributions for every cluster, and then the k-means clustering was basically trying to find the maximum likelihood estimation. And finally, I'm going to give you a bit of notes on how we can generalize, how we can validate, and things like that. Okay? So let's go ahead. So yeah, I'm feeling bad because I need to use the board, and then my voice is so now. Let's start with a motivational example. Okay, so what is the motivation? Let's say you remember the problem of outlier detection we talked about last time, right? So when we started with the idea of clustering, I told you, like, okay, I have a bunch of data points. We had this example of the bank, like the data you were collecting was the number of transactions per month and the amount of transaction. And we had this observation, there are two clusters. Some of them are like good people, rich people. Some of them are non-rich people, like normal people. And then we would say, okay, usually people are within these two categories, but there are some people like outliers, right? And then this is the case where, as a banker, you might be a bit suspicious about that, right? So that was the idea of outliers. So you have a bunch of data, you can see it here, and every single data is within one specific cluster, but suddenly you see one sample which is totally out of any of those clusters, right? And then we called it outlier. And we said one of the ideas of doing clustering is it simply means that we want to find out who is outlier, and then we just put the attention on that particular data, right? But the point is that if I want to do it, I need to somehow specify some sort of clusters, and then I need to have one cluster for the outliers, right? It might be the case, right? But this is not the best idea we can do, right? At least it's not the most intuitive thing we do. So the better approach is to do a bit of random process or stochastic analysis on that. So to get this idea, let me just have one funny example. So do you know this slot machine or arm machine? Have you seen that? So I hope that you never play with them, but like there's an arm and then you push and then it's a random thing. So you either win or lose, okay? And then if you win the money. If you lose the money, yeah? And most of the time you lose, so you lose more than you win. This is the whole trick. Like you pay more than you get. Oh, yeah, thanks. So this is not working actually.
Okay,
so,
I'll check the
yeah.
batteries.
No, I changed the batteries, but oh, okay. I can try. Yeah, sure. Go. checked it here. Shouldn't that? All of them are enabled.
Yeah, just give me a second.
Okay.
You can continue.
Yeah, sure, no worries. Take your time. Okay, so yeah, keep on going till. So that particular ARM machine, I mean, this is a kind of random thing, right? And the outcome of this random machine is either you win or you lose, correct? So if I push the arm, I either win or I lose. Now, the thing is that, say, you got this machine in one store, and every day one single guy, one independent guy comes and pushes the arm, and then either wins or loses, right? And then you see this is the statistics of your machine. So you make a data set, like first day the guy wins, the second day the player loses, third day loses, and so on, yeah? And now one guy comes and plays today, tomorrow, and the day after tomorrow, and always wins, right? Now the question that you have is whether this is a likely thing or not. So this is a better kind of specifying the outlier, because the outlier, it could be not a low outlier, right? So it could be totally a chance, like good luck, and then the guy just won over and over. No. No worries.
I'll just open it up from the back. Which team you have? Very good.
Okay, sorry guys. So, good, out of cage. That's the worst thing is teaching behind this place. Okay, now one example, for instance, is that you see 10 days, and then you see like the first day player wins, the, I don't know, fourth and fifth day it wins, but anything else is losing. And then some guy comes over and wins 3 days in a row, and then you wonder whether it's a typical thing or not, right? So if you think like that, and if you think like this 3 ones is a sort of outlier or a normal thing happening, then you are basically thinking stochastically, because you expect to see the guy, loses more often, right? Because your data is telling you that. So if you look at the data set, most of the time people are losing. So that is the idea. So if you want to write down this problem in a form of a learning task, so this is again a learning task. And what are the components of this learning task? What is the data set? The data set is basically the result that you have collected from the previous players, right? So that's going to be your data set, correct? And then what is the pattern you're seeing in the model? So what is that? Your stochastic feeling tells you that there is a certain chance for winning. And when you have this certain chance, if you exceed in one sample outcome, this chance, then you feel like it is a normal, right? So there is a certain chance for winning, and this is when you call it normal. If this is not the case, you don't call it normal. It could be just a good luck, as I said, but this is not typical, right? You get a bit suspicious. And what is the learning algorithm that you have? The learning algorithm is the one which is taking the data and computes for you this behavior, right? Whether it is normal or it is not. Yeah? But what I am doing is still a bit out of intuition, or it does not have a concrete definition. Because I have my data set, then I have, okay, this is the data set, that is okay, but then I want to make my model. I told you the model is a sort of function. And this function needs to get a data, so 1x, for instance, and then it needs to give you something at the output. What is that thing? Yeah? Okay, maybe I would say, okay, it's going to tell me whether it is normal to have this data, normal behavior, or anormal, yeah, or I don't know, non-typical, yeah. Is it typical or non-typical to have this particular x, right? And then you have your learning algorithm A, which is getting data D, data set D, and then is trying to find out what is the best guy, which is doing this decision making, yeah? But again, thinking of that particular model is not a very easy thing, okay? A better way of thinking it is to just follow the stochastic point of view that all of us have. So the better way is to think of it as a stochastic thing. This is the probabilistic viewpoint. And in that viewpoint, you look at this data to be sample coming out of a random process. So think of that game, that machine. So it is a random thing, right? Each time you push the arm, a random thing comes out. So it is either winning or losing, right? So what I can do instead of that, I can say that the pattern or the model that I have is that when I just push that particular arm, let me just take this off. If I push the particular arm, then I am seeing 1xn, right? This is the output of the game, right? And this is either winning, so I'm going to win, or I'm going to lose, right? Then what all of us have as a feeling, so winning is happening with some probability, right? Say I call it the probability theta, where theta is something between 0 and 1. Then what is the chance of losing? What is it? 1 minus theta, right? So this is the feeling that you have. And then what you see out of that data set, for example, you would say, okay, theta is approximately, for instance, 0.2. Meaning that if I see a guy playing, or independent guys playing 10 times, roughly 2 times they should win, 8 times they should lose. But if someone comes over and wins 10 times in a row, then this is a bit suspicious, right? This is an outlier. So what you have now, instead of a particular function, explicit function, which takes your input and gives you a deterministic explicit output, you basically have a distribution, right? So you think of your data as a random thing, random sample, and then you want to know what is the chance of this data being a win or being a lose, right? So what is the thing that you now need to understand? If you think of your samples of this form, what is unknown in this particular thing I have written here? Theta, exactly, right? So you want to know theta, right? Because if theta is 1, for instance, it means that anyone playing is always winning. So if anyone comes to you and plays 10 times and wins all the 10 times, you don't wonder, right? You only wonder when you know that this theta is 0.2, and you want it to be, but you see the samples, the one playing is always winning. This isn't then weird, right? So the thing that you don't know now is theta, and don't panic. I'm going to break it down for you. But now we're not going to learn an explicit model in this form, but we are learning this guy, right? And then I am collecting the data, so this is the first thing. The second thing is that I am assuming that my data is of this form. And the last thing that I want to do, I want to find a learning algorithm which starts from this data D, data set D, and it's going to tell me what is a good estimate for that theta. What is the right value that I should set for this theta, based on which I can then later on analyze whether something is typical or non-typical. Clear? So this is the probabilistic viewpoint. So I am going to consider one data set. I am going to assume that what I am seeing is coming from a random process. But the point is that I don't know what is the distribution that describes this random process. Okay? And then what I try to get my data set, design one algorithm which based on that data set somehow approximate that, or approximately describes the random process, meaning that basically I find that distribution, the distribution of that random process, okay? So as I said, don't panic. I'm going to break it down for you. Just I want to give you the idea of probabilistic viewpoint. So before I start, we just need to have a quick recap on some, basics of probability theory, just making sure that we're all on the same page, and then we keep on going with that. Any questions? Everybody's clear? No questions? Great. So let's start with the random probability. So first of all, everybody's clear about the random variable. What is a random variable? Yeah? So if I say x, which is a discrete random variable, it could be either a1, a2 till a, say, I. I think I have written I, right? Yeah. So it could be I different cases, right? Then, what does it mean when I say it's a random variable? So it could be a1 with some probability p1, right? And then it could be a2 with some probability p2, and so on till pi. Correct? Usually what I write is that x is distributed with p of x. And then this p of x is usually the one which I write down. I mean, it's a distribution, but it has a probability function with it. And that probability function simply is specifying these probabilities, right? So this is the probability of your x being a1, which I'm going to write it down p of a1. And so on for everybody. Clear? Yes? Now, if I sum up all of these guys, p1 to pi, what should I get? 1, great. Could they be negative? No. Yeah? And given that they should add up to 1, all of them are something between 0 and 1, right? Correct? So this is going to be the case. So this is the probability distribution or probability mass function of one particular random variable x, which is discrete, meaning that x could be either, for example, 0 or 1, right? So you have a probability mass function, and these two key properties are the Kolmogorov axioms. They should always be satisfied, right? So the probabilities should add up to 1. Each of them should be non-negative. That's it, right? So as I told you, this is a probability mass function, but what I'm going to do, I'm going to call it distribution. And you're going to see why, because I want to get rid of this discrete continuous always, okay? So this is the case for a discrete random variable. And let's consider one example. So here I have the Bernoulli random variable. What is a Bernoulli random variable? What is it? Do you know what that guy is? So if I write x is distributed with a Bernoulli theta, what do I mean? I mean that x is a binary variable, okay? So x could be either 0, 1, or 0. And I assume that the probability of 1 happening is theta, then what should be the probability of 0? 1 minus theta, right? And this theta should be something between 0 and 1, of course, right? So theta could be anything between 0 and 1, right? This is the Bernoulli distribution. Clear? So when I say x is distributed with Bernoulli, it means that if I just sample it, if I just look at it, then with probability theta it could be 1. With probability 1 minus theta it could be 0, right? So that's it. This is the Bernoulli distribution. So one example. Now, what if I have a continuous random variable? What's going to happen then? What about a continuous random variable, x? So say x could be any real number. So I'm writing x is distributed with p of x. What is the probability of x being exactly one value? For example, I don't know, alpha. What is the probability of this thing? It's 0, right? So if you have a continuous random variable, the chance of it being exactly 0, for instance, is 0, right? So I cannot define such a thing. This is useless. So what we define instead of that? The density function, right? How we define it? So I'm pretty sure all of you know it, but just as a recap. So I cannot compute this guy, but I can compute the probability of x being less than or equal by alpha, right? I can compute that one, correct? Yeah? If one random variable is uniformly distributed between 0 and 1, what is the chance of it being less than half? What is it? It's half, right? What is the probability of it being less than 0.7? It's going to be 0.7, right? It could be anything between 0 to 0.7, so it's going to be the length of that part divided by the whole length, which is 1. It's going to be 0.7, right? So you can compute this guy, and this guy is going to be a function of what? What could I change here to change the value of this probability? Alpha, right? So this is going to be a function of alpha, right? Do you know what we call it? What is it? Go ahead. CDF, right? Cumulative distribution function. So this guy is the CDF, cumulative distribution function. Huh? So you cannot define the probability of x being exactly alpha, so you cannot use it, but you can define this probability, right? And this is a function of alpha. What's going to happen if I send alpha to plus infinity? What is the value of this function? It's 1, right? The probability of one real number being less than plus infinity is always 1. Yeah, definitely. This is a real number, right? So this is going to be 1. What happens if I set alpha to go to minus infinity? It's going to get? To say it? It's 0, right? Because the probability of something being less than minus infinity is 0. I mean, nothing is less than minus infinity, right? So this is always going to look like this guy. So it's starting from 0 and then gradually goes up to get into 1. At some point it gets 1, or it just gets close to 1. So here is always 1. And this is going to be your f of alpha if you change the value of alpha from minus infinity to plus infinity. It doesn't need to be smooth, as I showed here. It could be a step-like or stepwise, step by step, any form. But at the end of the day, you start from 0, it ends up at 1. Okay? And now, what you can do, you can define instead of the probability mass function, you can define something that we call it the density function. And that density function, so P of one particular point alpha it is the density at the point alpha, which is the derivative of this CDF function at the point alpha. Okay? Clear? Now, if density is the derivative, what would be the integral of P alpha, d alpha? So if this guy is derivative of this one, what is its integral? F itself, right? So let me write it down in this form. Instead of alpha, I write you x here. And then it starts from minus infinity to alpha. And this guy is going to be exactly f of alpha. This is the property. Yeah? So what does this density do? You have a curve. If you start adding up all the surface under this curve up to point alpha, then you get the probability of being from very beginning to alpha, right? So this is what we call it probability density function. So this guy is now PDF, and then it has this particular property. And once you have the density function, you can again do the same thing as we did in the discrete case, right? So we can define, if we want to know what is the probability of x being, for instance, between alpha and beta, what do we need to do? We need to just look at this density function and integrate it between A and B, right? So integrated between the 2 points, this is going to give me that probability. So PDF itself is not a probability. This is a very crucial thing. Don't do such a mistake. This sounds very bad. But this is something that giving you the probability, right? And it's the density of the probability. Yeah? Okay? Okay. Now, again, you can have the same properties. I mean, P should be non-negative definitely because you want to integrate it to get a probability. Probability must be positive. So the function should lie above the line, right? So it's always positive. This is one point. And the other point is that if I integrate it from minus infinity to plus infinity, if I send this alpha here to plus infinity, what is going to happen? It's going to be f function at point infinity. Is the chance of x being between minus infinity and plus infinity, which is always 1, right? So it's the same thing as the summation you have in the other case. Okay? So this is going to be the PDF. We don't have probability mass function here, but again, I'm going to call it distribution. So from now on, when I tell you x is distributed with that distribution, if you know that x is continuous, simply think of the PDF. If you know that x is discrete, simply think of the probability mass function. Clear? Everybody's cool? So we are good? Should I go on? Great. So now let's just have one example of the continuous random variable. So this is the Gaussian random variable. I'm pretty sure all of you have seen it before. So usually I show it in this form. So x is distributed with a Gaussian distribution. That n comes from normal because Gaussian is considered to be the normal distribution for any continuous variable. So it's coming from a normal or Gaussian random variable with mean value, the average value mu, and the variance sigma squared. And what are these two guys? I'm going to talk about them shortly. Okay? Now, how does it look like? So this is a continuous random variable. What should I write down for it? PMF or PDF? PDF. Great. So I need to write down the density function. And the density function looks like this. Look at it. So it's 1 over the square root of 2 pi, the variance. Then it's exponential function e to power minus x minus mu squared divided by 2 sigma squared. Okay. Now, where is this function maximized? What should I put x to have this guy maximum? I should put x mu, right? When I put x to be mu, then the exponent is 0, meaning that that exponential is 1, and then the value is 1 over square root of 2 pi sigma squared, right? Correct? So if I said, so x is distributed normal with mean mu, and variance sigma squared. And this means that if I put value of x to be mu, then this guy is maximized, and the maximum value is 1 over square root of 2 pi sigma squared, right? And if I set this sigma squared to be very, very, very small, then this guy could be very, very, very large. And it could eventually get more than 1, correct? So no problem. It's density. It's not probability, correct? Now, do you know how does it look like? The shape? The bell? Great. So it's going to look like this, right? So it's a bell-like. And it's maximized exactly at mu. So you have high density at mu. Most of the time when you try realizing one sample, you're going to see it close to mu. And sometimes you can get out of it. So it has lower density. So you can have, again, the same interpretation as probability. But always careful, it's not probability itself, it's the density of it. Clear? Now, the variance, how you can find out about the variance depends on how this bell is shaped, right? So if I make the variance most of the time, so around 70% of the time, or if you compute the integral from mu minus standard deviation to mu plus standard deviation, so if you think of the average value and then you just go one standard deviation back and one standard deviation forth, then 70% of the time your variable is here. Yeah? So if you just randomly generate some Gaussian numbers, 70% of the time is between its average minus a standard deviation and its average plus a standard deviation. If you increase this interval to be 2 times standard deviation on each side, it's going to be 95%. If you make it 3 standard deviation, it's 99%. What does that mean? So say my random variable, say for instance, my mu is 1 and my standard deviation is also 1. Okay? So now if I think of the interval, so mu minus 3 sigma and mu plus 3 sigma is going to be 1 minus 3, so it is minus 2 and 4, right? This is the interval. So what does it mean? It means that if I have a random variable, Gaussian, with mean 1 and variance 1, 99% of the time I generate one random variable of that form, it's going to be somewhere between minus 2 and 4. It could be 300 as well, but it's going to happen 1 billion, right? Or trillion even. Clear? And you can go ahead, use Python, just generate with that random variable as much as you want, and tell me whether you see 300 or not. Okay? So I hope that it made it clear for you what is the density and what do I mean when I talk about the continuous random variable. The next thing that we have is the concept of independent random variable. So if you have 2 independent random variables, what does that mean? It means that there are 2 random processes happening independent of each other, right? So I push the arm and then there is a thunderstorm. Nothing has to do, my pushing arm has nothing to do with the thunderstorm, right? So they are happening independently. And what is the chance of both of them happening at the same time? The chance of the first one times the chance of the second one. So this is the definition of 2 independent things, right? So if x and y are independent, then the probability of them happening together is the probability of the first one times probability of the second one. And I say probability, but you do know if they are continuous, you just put instead of that p, the density function, correct? Everybody's clear? Now, you know what is the independent random variable, so what is IID sequence? IID sequence, I have x1, x2, x3 till xn. I would call it IID when every single guy is generated independently, so all of them are independent, and all of them are coming from exact same distribution. And what do I mean by that? Pushing the arm of the machine, right? If I do it 100 times, and each time independently, right? So I push it, I leave it, I again push it, I leave it, and so on. So 100 times I get Bernoulli things at the output. I either win or lose, and each of them is coming with the same distribution, right? The distribution of that machine, winning or losing, right? So what you should think of IID sequence is simply like random samples coming from the same distribution. Like I have one machine, always think of that as slot machine. The slot machine, you have it, and you randomly just try it as much as you want, okay? This is an IID sequence. Each sample you see is one sample of that machine. Clear? Any questions? Great. So if you got no questions, then let's just look at one simple example so I make sure that everybody's clear about the idea. So assume that I have one Bernoulli random variable, this slot machine. It has probability theta, so look at this part here, at part 3. So this guy, this is the Bernoulli distribution. Yeah? Each time I sample from it, do you get what I mean when I say I sample from a distribution? I mean I push the arm of that machine, okay? So you always think of distribution to be one machine, okay? And it has a button on it. Each time you press that button, it's going to throw you one number. And that number is one of the numbers it could give you. And the chance of that number being something specific is given with the distribution, right? So now if I sample from this Bernoulli distribution, yeah, I'm going to get 1 with chance theta. I'm going to get 0 with chance 1 minus theta, right? Now say I just do 5 times sampling independently. What is the chance of seeing this thing here? So 1, 1, 0, 1, 0. What is the chance of seeing the first one, given the distribution? Is theta. Great. What is the chance of seeing the second one? Theta again. What is the chance of seeing the third one, which is 0? 1 minus theta, and so on, right? And what is the chance of all of them happening together? I just multiply them, right? So you can write it down in this form. So it's going to be the chance of the first one, second one, third 0, fourth one, last 0. And then if you multiply them, you have 3 thetas for the 3 ones, and 2 1 minus thetas, which are for the zeros. So this is going to be the chance of all of that thing happening together. Clear? It's important because this is going to help us when we start with the likelihood. Oh, the battery is off now? Wow, today is a great day. So, okay, so everybody's clear about this idea, right? So we can do the same thing with the Gaussian, right? So maybe, for instance, I have one machine which is capable of generating Gaussian random variables, and it can generate Gaussian numbers which are whose average is 0 and whose variance is 1. Okay? Do you know any such machine? You're a Python compiler, right? You can do it. Just go to rand n, just generate one random number. And if you generate rand n, it's going to be a normal random variable, Gaussian random variable with mean 0 and variance 1, right? So I have that machine. I push the button 3 times, and I get 3 different random outcomes. These are the random outcomes. Now, what is the density? Now, we don't have probability, obviously. We have density. What is the density of all of these things happening together? I just recall the distribution. What was the distribution? So this was the distribution. This is the mean value is mu is 0, and variance sigma squared is 1. So P of x is going to be 1 over a square root of 2 pi. I don't have anything here anymore. E to power minus x squared divided by 2. Correct? This is the density, right? And then what should I do? I should take the first value, 0.3, put it here. I take minus 1/2, put it here, and so on, right? And once I computed all the 3 values, what do I do next? I multiply them, right? So it's like I have this distribution. I look at its value at the 3 points, those blue dots, and then I multiply them to each other, it's going to be this value, okay? So this is basically putting that x to be 1, 0.3, 1.5, and minus 0.1, okay? Everybody's clear? Cool? Great. So now that you have the idea of IID sequence, what do I mean by expectation? Do you know what is the definition of expectation? The expected value of one random variable. So if I have one random variable x, which is a discrete random variable for the moment, okay? If I want to compute its expectation, so I'm going to compute the expected value of x. How do I do that? I'm going to look at the outcomes that x could have. So here, it could be A1 with probability PA1, right? It could be A2 with probability PA2, and so on. So I'm going to get every single outcome that it could have, multiply it with its probability, and then sum them up, correct? So it's going to be the summation over all possible x's that you could have, x times p of x. Clear? Now, if you don't have a discrete random variable, then obviously you should go for a density function, right? And then you replace that summation with integral, right? Now, if instead of x itself, I have a function of x. So I want to compute the average of a function of expected value of a function of x. What should I do? I replace x with f of x, right? So I'm going to replace this guy with f of x. So that is the definition of expected value. But the definition is not important. The more important thing is the meaning of this expected value. What does it mean when I say, for example, the expected value of one random variable is 1? So IID sequences are going to help us to understand that meaning now. It simply means that if I just try that random variable n times, and then I average what I see, then it should be roughly 1. And it's going to get exactly 1 when the number of samples I'm collecting is going to infinite, right? So meaning that if I have, for example, a slot machine and its average is half, it simply means that if each time I push it, I either get, for example, 0 or 1, and then 50% of the times I'm getting 1, right? Almost. Everybody's clear? So you got the idea what is expectation? This is why we call it expected value or expectation, because you expect anything in this argument to give you this value when you try it for so many times, right? If I try one random generator only once, it could be very variant, right? But if I try it 1,000 times and then I average everything out of it, it could be roughly its average, right? Clear? Great. So let's just look at one simple example. So example of the Bernoulli variable. So again, look at the Bernoulli distribution. So it could be either 1 with probability theta, or 0 with probability 1 minus theta, correct? So if I want to compute the expectation of that guy, so if x is generated Bernoulli with probability theta, then what is the expectation of x? It is going to be 1 times its probability, which is theta. So 1 times theta plus 0 with this, times its probability. The 0 times 1 minus theta, which is theta, right? So the average of a Bernoulli variable is theta. Now, what does it intuitively mean? It means that if you get that Bernoulli random generator, the slot machine, and you try it 1,000 times, and then you count the number of times you see 1, for example, you win. And then you divide it by 1,000, it should be roughly the value theta, right? Yeah? Makes sense, correct? So if the slot machine has the chance of winning 0.2, it means that when you just push the arm, 20% of the time you win, 80% of the time you lose. 20% 1, 80% 0, that's the average, right? Clear? So same thing you can do with the Gaussian variable. So I told you mu is the mean value. It means that the expectation of the Gaussian variable is mu. Meaning that if I put x to be, so if x is normal with mu and variance sigma squared, then the expectation of this x is going to be mu. And this means that if I take the integral of x times that particular function you have, the p of x, yeah, that particular function, I can write it down for you here. Square root of 2 pi sigma squared e to power minus x minus mu squared divided by 2 sigma squared dx. If you compute this integral, it is mu. You can go ahead, do it at home if you don't buy it. I'm pretty sure most of you have done it before, but if you have not done it, just try it. You can do it by integration by part. And then this is going to be mu exactly. Or for example, I told you sigma squared is the variance. And definition of variance is the expectation of x minus the mean value, the average value, which is mu here, squared. So if I replace x here with x minus mu squared, and I compute the integral, then it's going to be sigma squared. And again, if you don't buy it, just go home and compute it. It's a bit more trickier, but you can do it. Everybody's clear? Yeah? Great. So that means that is from the definition point of view, but again, intuitive meaning simply means that if you just collect lots of Gaussian variables, so you have this random generator which works Gaussian, and you push the button 1,000 times and look at all the numbers you have seen, if you average them, it's going to be mu. If you compute the sample variance, meaning that you get every single number you have seen, subtract it from the mean value, square it, and then average that number, then you're going to see sigma squared, right? And this is how you do it in practice, right? So in practice, you don't know really the variance. If this is coming from a true natural thing, you just look at the samples and you try to estimate it. Everybody's cool? Clear? Great. So last thing about this review is about the other kind of random objects we could have. So what I wrote on the board, it was a random variable, meaning that I'm thinking of one number generated randomly. But your random thing is not supposed necessarily to be a random number. It could be any object, right? It could be a vector, right? A random vector is a vector whose entries are generated randomly. A random matrix is a matrix whose entries are random variable. A random text is a text whose characters are generated randomly. A random image is an image whose pixels are generated randomly. So as long as you know random variable, anything else, you can always randomly generate, right? But you can't have a super duper big random object, right? Very high dimensional. And everything inside that is a random thing. So you can think of that, and whenever I say x is distributed with p of x, what I do mean, I mean that that random object has one distribution. It could be density, it could be PMF, mass function, but depending on whether it's discrete or not, but it's a distribution, right? So it has a distribution which is going to tell you what is the chance of this particular object being something, right? Okay, if it's a vector, it's the joint distribution of the entries, matrix, so on, so. But for you, in this lecture at least, always think x is a number, okay, unless I tell you, okay? That's going to make life easier to understand, and everything really extends to a higher dimension. So, everybody's cool? Great. So, hopefully we are now on the same page. But if you didn't get what I'm saying, please ask. This is important. I want you to understand what is maximum likelihood. Really, I want. Okay? So, now let's go ahead back to this formulation. So, I have tried to gray everything out, but the quality is not good enough. So, let's just focus on the second bullet. Okay? The second bullet here. This is what I told you when we started. I told you that the modeling that we do, the probabilistic modeling that we do, is that we look at the data and then we try to model it as a distribution, right? And then what we want or model is basically the distribution of that random process, right? And then we try to train that model. We want the learning algorithm which looks at the data and specify that model, which is the distribution now. Now we can formulate it using the notations we have introduced. So let's go ahead with that. So for instance, say I have one data set of this form, right? So those x's inside this could be anything. Just remember the example I told you, winning, losing, right? In that case, these x's are binary, right? So if I do know that this machine which is generating win or lose is a random thing, it's going to give me either 1 or 0. 1 happens with 1 probability, 0 happens with 1 probability, right? So I can describe this machine by Bernoulli distribution, right? I can say this machine is a Bernoulli random process, and whatever I see is a sample from that process, correct? But what is theta in that? I don't know. I look at my data set and try to find it out, right? Or for instance, somebody tells you these numbers that you see are coming from a Gaussian distribution. But what is mean and variance? I don't know. Yeah? So what you can say is, at the end, you can say this is a Gaussian distribution with a mean and a variance which I don't know. Yeah? So you can model it with that distribution, and then you want to use your data set to find out what is the right choice, a good estimate for the mean and variance. Clear? So this is what I mean by modeling the distribution. Okay? Now, in general, if I talk about the distribution, I can write it down in this form. So I can think there exists one distribution. That P you see here, that P is, for instance, the density of a Gaussian distribution. It is a Bernoulli distribution. Yeah? And this guy is parameterized by some theta. What is theta? For instance, this value of theta that you have in the Bernoulli distribution, or the mean and variance of the Gaussian distribution. Okay? So it is parameterized with that. You don't know those parameters, but you know the distribution. Or you're assuming that. I mean, this is coming from a natural process. Most natural processes are Gaussian, so I am assuming this is Gaussian. Yeah? I can do it as well. Clear? So what I think that the samples I'm seeing are coming from a specific distribution, P theta of xn. Clear? So let's just make one example. So the Bernoulli example, I assume that I have binary numbers, and these binary numbers are the output of the games that I have played, or different players have played, right? So anyone who plays is either winning or losing, right? Now, maybe I assume that the game is random. So the game has some component of randomness in it. Okay? So the outcome is a random process. And everybody who is playing is simply going to that random process and sampling one sample from it. Right? Now, since it is a Bernoulli or binary random variable, it could have only a Bernoulli distribution, right? As long as I believe everybody who is playing is doing it independently, right? Which is mostly the case. Correct? So, if this is the case, then what I can say that whatever is coming from this guy, from this machine, from this game, is a Bernoulli random variable, a Bernoulli sample, and this sample could be 1 with probability theta, and it could be 0 with probability 1 minus theta. Correct? So I am specifying the distribution. So now I'm looking at that slot machine as a Bernoulli distribution. But what I'm doing here is that I am just leaving theta to be freely chosen, right? So I can choose theta. And how can I find out what is the right choice of theta? That is what the learning algorithm is supposed to do for me, right? So it's going to start from the data set that I have collected. So I have played with this machine 100 times, and then I just collect the record of my winnings and losings, and then now I want to use that in order to approximate what is theta. I mean, at the end of the day, like any other machine learning thing, we cannot find the exact right choice of theta, of course, right? But we can approximate it, right? Or estimate it. Correct? Everybody's clear? So this is going to be the case. Now, one thing that I can say I have collected one data set consisting n different samples, okay? If the samples are happening independently, what is the chance of seeing that data set? So the chance of seeing that data set, the chance of seeing the data set D is, which is parameterized by theta, is the chance of having x1, x2, and so on till the last guy, right? But I told you x1, x2, all of them are independent. So when they are independent, how can I write them down? Product of the probabilities, right? So I can write it down, P of theta x1 times P of theta x2, and so on till P of theta xn, correct? Now, I told you this is a Bernoulli variable. So x, all of those samples, x's in my data set, they are either, what are they? 0 or 1, right? So if they are 0, what should be this P theta of 0? 1, right? No, P theta of 0, 1 minus theta, correct. If it is 1, what it should be? Theta. So if you look at this, how many theta are going to show up? As much as ones you have in your samples, right? How many zeros, 1 minus thetas are going to show up? As much as zeros you have, right? So I can write it down to be theta. This is when my xn is 1. And here it's going to 1 power. What is the exponent? Number of ones, right? Number of ones that I have. Times, I have 1 minus theta. And how many times that is going to show up? Number of zeros. So it's going to be to the power of number of zeros, correct? So this is what you see in the slide. Okay? So now that I have modeled my outcome of the slot machine by a Bernoulli random variable with theta, and I assume everything is independent, now I can write down the chance of seeing that particular data set. Clear? And again, what is unknown to me here right now? Theta. Great. So theta is not known to me because nobody told me. I just assumed that model. Yeah? So one other example, the Gaussian example. So say, for instance, I have lots of numbers in my data set, and I do know that all of them are coming from a Gaussian random number generator. Okay? I might do know it because somebody told me, or I might just simply assume because I have no other choice. Yeah? So, or maybe I just had before some statistical analysis. I collected lots of samples, and then I just plotted the histogram, and I see, oh, this is very bell-shaped. So probably a Gaussian distribution is a good approximation. Clear? So I do that, and now what can I say? I can assume that every single data point that I have inside my data set is coming from a Gaussian distribution. The average of this Gaussian distribution is mu, and the variance is sigma squared. What are those mu and sigma squared? I don't know it yet. Okay? I don't know that. But I can assume that, right? Clear? Now, if I see my data set, again, the whole data set that I have, which is x1, x2 till xn, can I compute the density now for this collection of data? Can I do that? I mean, exactly the same thing as I have here, right? I would say x1, x2 till xn, all of them are Gaussian variables, right? I assume they are independent, so I'm going to get the PDA if I repeat it n times, multiplied next to each other, right? And what is the unknown here? What is yet to be explored? Mu and sigma, right? So these values, mu and sigma, are not known to me, but if I just think of 1 mu and sigma, then when I have my data set, I can write the probability of that data set to be, or the density of that data set to be of this form. Clear? Everybody's cool? Any questions? No? Great. So this is what I can compute, and one just illustration of what I'm telling you here. So when I think of one normal distribution, it means that I assume that I have this bill, but I don't know how exactly I should squeeze it, for instance, or where should I put the peak of the bill, okay? So if I change mu, this bill is going to go right and left. If I change sigma, it's going to get squeezed or stretched, right? Clear? Yeah? But if once I fix it, so I say mu is 1, sigma squared is 2, then I have the bill, and then I can compute the thing I computed here, right? So if I know mu and sigma squared, I can compute exactly what the number is. Clear? Great. So do you want 5 minutes break? So you just have a bit of refresh. Yeah? Okay. So 5 minutes and then keep on. No. So the first assignment I'm going to upload it tomorrow. Okay. Yeah. And then the lecture of the last time, you can watch it online. Okay. If you get to the correct page, there's a link with that.
You mentioned there were tutorials?
Tutorials was yesterday. So it was the first tutorial, but it was just basic things. So it's going to be always on Monday, so if you check the characters, then it's this. Yes. So on Mondays, it's 7 to 8. Okay. Yeah, yeah.
I really like UofT. So I'm still thinking about whether I need to take the applied learning course today. I'm not sure it's very useful for me.
I mean, it depends. If you had any course in deep learning before.
I have taken 2.
Okay, then.
That's fine.
It's just basically.
But actually, you mentioned the prescription, right? Perception.
Perceptron.
The perception. That is my first time to hear the perception.
Yeah, many people don't start with that. It's just a background. But then MLP, CNN, RNN.
Yeah, I just used ChatGPT to search that, so it told me that is the basic. I mean, the foundation for the MLP. Thank you. It's a new knowledge.
Okay, shall we go on? Okay, let's go on. So now, if I have this particular distribution, I assume this particular distribution for my samples, then this guy is modeled as the distribution with some parameter theta. So I don't know theta, but once I specify theta, then I can compute the probability or density of that particular sample xn, right? Okay. Now, we define something that we call it likelihood. So what is likelihood? The likelihood is the probability of your data set happening, the data set D that you have, the probability of your data set happening, assuming that particular distribution that you have assumed, right? So let's just take a look back here, for instance, or maybe here even easier in the Bernoulli case. So the likelihood of your data set is basically what I have written here for you, right? This is the likelihood of your data set. Why? Because if I assume that the probability of 1 happening in this Bernoulli random variable is theta, then the likelihood of that, or the chance of that data set happening, is basically this expression. Correct? Now, for the Gaussian case is again the same thing. So my unknown, the theta, is basically that mu and that sigma, right? Both of them together are the unknowns that I have. So for a given unknown, I can compute the density, correct? And then if I just look at the whole data set, and then I compute the whole density, then I'm basically computing the likelihood of that mu and sigma. Okay? Now, likelihood is the probability of your data set happening under this assumption that your unknown is the particular value, theta. Now, what is it a function of? Your likelihood is a function of what? What are you computing the likelihood for? Are you computing the likelihood of your data set? Any answer? Any suggestion? Am I computing the likelihood of my data set? No. Yeah? So this is a very important point. You are not computing the likelihood of your data set. You're computing the likelihood of unknown, the theta. If I assume theta is something, then I can compute that probability. The data set is something fixed given to you. The only thing unknown to you is theta. So this expression that you have here, the likelihood, is only a function of theta, correct? So you are computing the likelihood of theta. Don't do this mistake. Don't say that I am computing the likelihood of my data set, because you can't compute the probability of your data set, the density of your data set. You cannot compute a likelihood for that. Likelihood is for something that is unknown. Okay? Clear? So look at this function here once again, the Bernoulli case. So the one which I compute, the probability of the data set, that one is only a function of theta, right? Because my data set is known. I can count the number of ones, I can count the number of zeros, then I can put it in that expression, and this is only going to be a function of theta. Likelihood is only a function of your unknown. Same thing here with the normal distribution. The likelihood is only a function of mu and sigma, right? There's going to be only a function of that, and this is what we call it the likelihood of mu and sigma. Okay? So just to recap this again, so again, we have this particular example. So we talked about this. This is exactly the same thing that I showed you. This is going to be the likelihood, right? So if I have this data set, which is a Bernoulli data set, I assume this is coming from a Bernoulli process, and then I assume that the probability of 1 happening is theta, I assume that the probability of 0 happening is 1 minus theta, then I can write down the probability of my data set, which includes 3 ones and 2 zeros, right? Each one is happening with probability theta, each 0 is happening with probability 1 minus theta. Then probability of all of this data set happening all together, so I see 3 ones and 2 zeros, is theta to power 3 times 1 minus theta to power 2, correct? Now, when I compute this probability, this is going to only be a function of theta, right? And this is the likelihood of theta. Clear? Everybody's clear? Right? So you have to pay attention. Your likelihood is a function of your unknown. Now, one question from my side. Is it a probability on theta or not? Be careful when you answer. And don't worry if you do a mistake. Is it a probability of theta? It is a PDF of theta. If I integrate it over theta, does it end up 1? No. This is not the probability on theta, yeah? It's a probability on x, right? It's not a probability on theta, correct? Everybody's clear? So don't do that mistake, because your theta is something defining your distribution. You are not computing any probability on theta. You are not finding the chance of theta being 0.2. No, you're computing the chance of your data set happening, assuming that theta is 0.2. Clear? Okay, so if it is not obvious to you right now, I mean, as I said, don't worry about that. This is totally normal. So if you look at the McKay's book, and I think in chapter 3 or 4, he has given a big hint in a box. Pay attention, likelihood is not a probability, okay? So no worries in that sense, but think about it once again when you're back home, okay? Just try to make sure that you understand this likelihood is not a distribution on theta, okay, on the unknown. But rather than that, the definition is quite obvious. So you compute the probability of the data set, and you leave the unknown to be free, and then that function of unknown is the likelihood of your unknown. Same thing you can do with the Gaussian case. So we have this example of the Gaussian. So assume that you have a Gaussian random variable. What you do know, for instance, is that this is coming from a Gaussian, these 3 numbers are coming from a Gaussian random variable with mean mu and various sigma, but you don't know neither mu nor sigma, okay? What you can assume that the PDF is the PDF of a Gaussian with a unknown mu and unknown sigma, right? And if this is your data set, you can simply go ahead and replace those numbers, 0.3 minus 1.5 minus 0.1. You can replace it into the Gaussian distribution, and then you can multiply those three different values you compute, and then you're going to end up with one function, which is only a function of mu and sigma, correct? And this is the likelihood of mu and sigma. Again, this is not this density on mu or sigma, right? It's the likelihood of sigma, which could simply integrate something more than one, right? Everybody's clear what the likelihood is? Now, why we call it likelihood? So if I have one sample Gaussian thing, okay? Well, what was the last? 8, 9, okay. If I have a sample Gaussian, okay, say I have one Gaussian number, which is 1.5, okay? This is one sample thing that my data set has only this guy. Okay, this is my data set. So what would be the likelihood of this data set? Yeah? And say I know that X, I assume this model, it is sampled from a normal distribution with mean mu and variance 1. So I do know the variance, the only thing I don't know is mu. Okay? Now, what would be the distribution here? What would be the PDF? I can write it down, right? The PDF of that particular thing I have inside my data set, assuming 1 mu. So I don't know mu, I'm going to keep it as a free parameter, right? It could be any real number, correct? So I assume 1 general mu, and this guy is going to be 1 over square root of 2 pi. Sigma squared is, look at it, it is 1. Look at it here. So I assume that the sigma squared is 1, correct? So it's going to be 1 over 2 pi, and then multiply by e to power minus x minus mu squared divided by 2 times sigma squared, which again I do know is 1, right? Clear? Now, if I plot this guy, how does it look like? Yeah, first of all, let me compute the LD of mu. So the likelihood of mu is simply this guy when I put my x to be exactly 1.5, right? So it is going to be 1 over square root of 2 pi e to power minus, here I have 1.5, right? 1.5 minus mu squared divided by 2. This is my likelihood, correct? Correct or not correct? No? Yes? Everybody's clear? Now, if I specify mu, then this is going to be a distribution at point mu, right? Okay? This is P of x that I get, correct? If I specify mu, then my distribution is a normal distribution around mu, correct? And my value of x is 1.5, right? Say, for example, it's here. It is 1.5. This is the value of my distribution, right? How is it depending on mu? If I just play with this mu, this bell is going back and forth, and the value of density at this point is going up and down, right? And this is how the likelihood is changing. Clear? Everybody's clear? Any question? So you got the idea what I mean by likelihood? So, yeah?
Sorry, I might be really tired, but I thought the answer would be 1 because your data set only has one value.
Answer to what?
Like, I thought the answer to what would the likelihood be would be 1 since you only have one value.
No. Don't do that mistake. So I'm saying likelihood of mu, not data set. I said data set has no likelihood. Likelihood of mu, yeah? So what do I mean by likelihood of mu? I would say if I assume mu is, for instance, 1, yeah? Yeah? Then I have one distribution, right? Which is a bell around 1, correct? And then the density of 1.5, I can compute it, right? This is going to be the likelihood of 1, right? You got it?
But isn't your y the probability of x?
Sorry?
What's the y-axis?
Probability of x, exactly. P of x. This is P of x. So this guy is P of x, exactly. Yeah? But I am not computing I am computing P of x. So, I define the likelihood of, say I have only one sample, okay? So it's only xn. Then of mu, this is going to be P of mu xn, correct? So I'm saying that mu is the average. Then I put the sample that I have seen, 1.5 here. That value is the likelihood of mu, not x. Okay? And now, if I play with mu, then this bell is going back and forth. This likelihood can go up or down.
I agree. I think I'm just getting a little confused because don't you only have one x in this scenario?
Yeah, of course. I just did it for simplicity. But then we are going to just make it larger, of course.
Oh, okay.
Yeah?
So I was going to say, like, your y value can only have one value.
It's going to have one value, right? But what do you mean by that?
Like, it can't be a bell curve if your data set only has
No. Yeah. At the end of the day, if you look at this guy in terms of mu, in this particular example is again a bell curve. But forget about that. Just think of this px. You're right. I am talking about this one value. This is the guy here. But this one value could go up and down if I change this mu, right? This is the thing that I can tune. So if I just push it here, so if instead of this one, now I just change mu. So this is one choice of mu, say mu1. Now if I change mu to be here, this is mu2, then my bell curve gonna be this one, right? And then this one value is going to be this guy, correct? Yeah, okay. So this is the likelihood. Now, why do I call it the likelihood? Because I look at my data set and I would say, okay, if I assume mu is that, then the chance of this data set happening is this one. If I assume is mu is another thing, then the chance of this data set is happening is the other one, right? Like in that curve we have on the board, if I assume mu1, the white circle, this dot, this is the chance of the data set happening. If I assume mu2, the chance of data set happening is this one, right? Clear? This is why I call it likelihood. How likely is that data set to happen? Everybody's clear? Great. Okay, so key point, likelihood, only a function of your unknowns. Now, one question now. Say that we modeled one process. Okay? I got the process. I do know how kind of distribution it could have. Bernoulli, for instance. I don't know what is theta, right? So I'm going to assume some general theta, right? And then I write down that likelihood, which is a function of theta. Then, given the data set that I have, what should I take as the estimate or approximation of that theta, the unknown? Just think 2 seconds about that, right? Exactly. Yeah. So everybody sees that point? Because this is the crucial point. If you see that, everything is over. The likelihood is somehow telling you how likely is that parameter theta is some specific value, right? Given the probability of that data set, right? So what should you choose as theta? The one which is most likely to be, right? Correct? Everybody's clear? So in this particular example I have here, the Gaussian one, okay? This white dot is giving you the likelihood of theta being mu1, or sorry, your mean being mu1, okay? This red point is giving you the likelihood of your parameter being mu2. Which one is more likely? Mu2, right? Do you choose mu2 or mu1? Mu2. And now, forget about everything. You have only one sample, and that is 1.5 from a Gaussian distribution. What do you think, or what can you approximate as its mean? 1.5 itself, right? So because you haven't seen any other sample, right? So you would say the most likely thing that could ever happen is something very close to the mean value, right? Most of the time it should be very close to the mean value. So you're going to get your bell and just push it as much as you could. So you put it exactly on this 1.5, and there the likelihood is maximized. So if you just change mu more or less, the likelihood is less than that, right? So this is going to be the one who is maximizing your likelihood. So in general, the idea is that when you have one unknown theta, then you go for, you approximate or estimate that theta to be the value which is maximizing your likelihood. Clear? Everybody's clear? Any questions? You know you can ask questions? Better to ask questions than just go home late night without understanding maximum likelihood? Yep.
Just for an example, like what if they have like multiple 2x times?
Oh yeah, yeah.
Like what like flower would do?
We're gonna solve it. We're gonna see, yeah. But this is actually the interesting point when you have multiple data points. But what does the intuitive answer? What is the intuitive answer to that? Average, yeah. We're going to see that the maximum likelihood is the average. Yeah? So basically, whatever you do is maximum likelihood always. Yeah? So empirically, we are always thinking maximum likelihood for simple problems. For hard problems, we cannot really think of something. This is why we developed the maximum likelihood strategy. So, great. So this is the idea of maximum likelihood. So what does this likelihood do for us? So likelihood is a function of the unknown. And the unknown was something which specifies our model. And if you remember when we wanted to do the clustering, we had a bunch of unknowns. And then we wanted to define some metric which tells us whether those unknowns, the centroids, are optimal or not. Then we define distortion, right? We define distortion, or the risk. And then we say, okay, the optimal guy or the optimal centroids are those who are minimizing this distortion or risk, right? You're going to see that that is exactly likelihood, okay? So that distortion is basically the likelihood of your data set, unknown. I did the mistake, the unforgivable mistake, I did it, okay? Okay, so let's just look at the maximum likelihood first. So I told you likelihood is the density or distribution, probability or density of your data set. So x1 to xn, all of them happening all together, given that you're assuming some probability density function p theta, right? And then what we think that those samples are coming independently from the same distribution, right? So x1, x2 till xn, all of them are independent realization of the exact same random process, okay? So if we assume that, then we can simply write down that joint distribution to be the product of all the distributions. So I have not cleaned it yet, so it is on the board yet, right? So the probability of the data set is going to be the probability of all the samples we have seen. And assuming that they are coming independently, I can write it down the probability of the first guy times second guy and so on till the last one, right? So this is the product of all those probabilities, yeah? Sometimes we call one of them, so that p theta of one sample, we call it the likelihood of theta given that sample, okay? Ln, yeah? And it's nothing specific. I mean, your data set likelihood is simply the product of those sample likelihoods, right? Everybody's clear? Yeah. So based on the feedback I get from you, so there is a binary process. Either you are not clear or you are super tired. Yeah? My experience cannot tell me which one is the correct. So the likelihood, you can compute it later today, okay? But really, any questions? We're good to go? Great. So now I want to just maximize. I told you I want to find the theta which maximizes this likelihood. And this is basically written in the form of product of probabilities, right? And now what I can do, I can use the log trick. And the log trick, what is it? If you have a function which is non-negative, okay? And you want to maximize it, doesn't matter if you maximize the function itself or its logarithm. Logarithm is an increasing function, right? Defined on positive x's, right? Positive arguments. So if you increase one number, its logarithm also increases, right? If you decrease it, it again decreases, right? So if the logarithm of one function is maximized, this means that the function is maximum, right? If the function is maximized, the logarithm is maximum, right? Same thing. So instead of maximizing the function itself, I can maximize its logarithm. And why I'm doing this? Any reason? Any clue why I'm doing this? I want to maximize that guy on the top. This is a product. If I compute the logarithm of a product, it is sum of logarithms. That's going to be easier, right? So this is the only reason I'm doing. The number is going to be easier. So I can just write down the logarithm, the log likelihood. This is what we call it, the log likelihood. Instead of having that product, I can compute the log. And log of product is sum of the logs, right? Everybody's clear? Yeah? So what I am going to do, I am going to compute the log likelihood of every single sample I have in my data set for a given unknown parameter theta, and then I sum them up. I try to maximize that term in terms of theta. And if I find the maximizer of that, this is what we call it maximum likelihood estimation. You got the idea? If you got the idea, I go ahead with an example. No? Any questions? No question. Okay. So let's look at this example. Maybe that makes everything much more clear. Now, this is the data set that I have, right? So 3 ones, 2 zeros. I assume, so my model, what is my data set? So my data set, so what is it then? 9, 10, 11. So my data set is of this form, so it is 1, 1, 0, 1, 0. What is my model? What is my model here? Please? This is Bernoulli, right? So I assume these samples are coming from a Bernoulli distribution, right? Meaning that I assume P theta of any of those x's is theta when x is 1, and it's going to be 1 minus theta if x equals by 0, right? Correct? So we computed the likelihood. So the likelihood of this data set for the specific choice of theta. What is this likelihood? So we computed that, right? This is the probability of 1 happening, so it's going to be theta times, again 1 happening is theta times 0 happening is 1 minus theta times 1 minus theta. So this is what we computed a couple of times. Theta to the power 3, 1 minus theta to the power 2. Clear? Right? Now, I want to maximize this guy, right? So I want to find a theta, a choice for theta, which maximizes this likelihood. And I told you better to just go for logarithm of the likelihood, right? So what is the log of the likelihood in this case? Log of this guy, it's going to be log of the first one plus log of the second one. And this is theta to the power 3 is 3 log of theta. Everybody's clear what I'm doing? Yeah? So it's going to be 3 logarithm of theta plus 2 logarithm of 1 minus theta. You're fine with that? Yeah? Now, I want to maximize this guy. I want to find the arg, so my maximum likelihood estimate is the arg max over all possible thetas. What can be my theta? What are the choices possible for theta? Can it be 5? No. It should be something between 0 and 1, right? So I'm going to look within the interval 0 and 1, and I see which one is going to maximize this function. 3 log of theta plus 2 log of 1 minus theta. Clear? Any idea how I can maximize that function? So for those of you who know a bit of optimizing, this is a convex function. But in general, I mean, remembering from high school, if you have a function of one variable, how do you find its maximum or minimum? Yeah, go ahead. You compute the derivative, you set it to be 0, right? These are the candidates for being the maximum or minimum. In this case, you have just one, and that is the one which is maximizing it. It's a very nice function, okay? So if I go ahead and compute the derivative of this 3 log of theta is going to be, so let me call this whole thing to be s of theta, and then the derivative of s with respect to theta, this is going to be, can you help me doing that? Make sure that everybody's following. What is the derivative of the first term? Derivative of log of a theta is 1 over theta, yeah? I assume that log is natural, so in the natural base. So derivative of log is 1 over theta, so it is 3 over theta, okay? What about this one? 2 over 1 minus theta, and then I need a minus 1, because the argument is minus, right? So if you are not following, just please double check it at home, but then it is going to 2 minus 1 theta. Minus 2 over 1 minus theta, okay? Okay. Now, if I write it down, it's going to be theta, 1 minus theta. So here I am going to have 3 minus 3 theta minus 2 theta. So it is going to be, at the end of the day, 3 minus 5 theta over theta 1 minus theta. Now, I want this guy to be 0. What should be theta? I mean, nominator should be 0, right? What should be theta? So now I'm taking it personal, because everybody knows what should be theta. It's 3 by 5, right? So it's going to be your theta star, this guy. I mean, out of it, you find out that theta star is going to be 3 by 5, right? Does it make sense to you? Look at the data set. Does it make sense to you? Right? Should theta be, I mean, do you approximate theta or estimate theta to be 3 by 5? You had 5 experiments, 3 of them are 1. What is the chance of having 1? A basic question, right? 3 by 5, right? So if you go ahead and do that optimization, you're going to see that exactly what we did here. The maximizer is 0.6, which is totally consistent with what you would think if you wanted to just do it naturally, okay? Any questions? Same thing you can do with a Gaussian thing. So I have given this Gaussian in this slide, so I don't want to just do the optimization again right on the board for you. Just wanted to have one example that you have it. But this is quite a simple example. So look at this guy. So I assume that these data points are coming from a normal distribution. The mean value is unknown, but I know the variance. The variance is 1, okay? Now, the only parameter that I don't know is mu, right? And I want to estimate it. I want to do maximum likelihood. But before I start maximum likelihood, what do you expect this mu to be? Your estimate. I give you 3 numbers. I say it's coming from a Gaussian distribution with mean mu. I don't know mu. What is your estimate of that mu? What is it? You can average them, right? You just go ahead and average. Mu is the mean value. Mean value is the average. So basically, you just average them, right? So this is what you do if you have not heard of maximum likelihood at all, right? And now, if you go ahead and do the computation, so the likelihood of mu is basically this term, which is the probability, assuming this particular distribution I have written here. So this guy that I have written here, P mu of, oh, I forgot this x here. So P mu of x is given with this term, right? And then once I put x to be 0.3, once I put in minus 1.5, minus 0.1, and then I have three different things, all of them function of mu, I multiply them next to each other, right? And then I'm going to have that term, 1 over the square root of pi to power 3, that is not important. I have the other one, and the exponents get added up, right? And I want to maximize this guy. You can do it without any of those derivative or other things, right? How can we do it? If I want to maximize this one, where is mu showing up? It's showing up only in the exponent, right? And the exponent is negative. If I want to maximize this term, what should I do to the exponent function? Minimize it, right? If I minimize that exponent function, since it's getting multiplied with minus, right? Then it's going to make everything maximized. Now, potentially make it 0. Yeah, that is the best thing you could do. But you don't need to use this intuition. You can just simply compute the logarithm. And once you compute the logarithm, you have one term, the first term, which is coming out of the constant. It's not a function of mu. You can forget about it. You have the other term, which is the component, right? And I want to maximize this function. I can simply minimize its minus, right? So I get rid of that minus as well. Now, you have three different numbers. You want to find a mu which is in minimum average distance from all of them. What is the mu? The center of them, right? So you just average them out. So you can go ahead at home. You can try it, and you're going to see that mu, the optimal mu, which maximizes this term, is exactly the average of 0.3 minus 1/2 minus 0.1. Okay? And that is exactly this 0.63 something, 29, I guess, and you go on. Yeah? So, again, maximum likelihood is just doing the obvious thing, right? Everybody's clear? Yeah? Any question? Oh, by the way, I guess there is a mistake here, right? So it shouldn't be that. How is it possible? So that is minus 1.5. It should be minus, right? So I have done some mistake. Probably I have considered 1. I guess 1.9. I don't know what I can say. Oh, I think in your lecture notes I have other numbers, right? No, not in the set. Look at the likelihood. I think, yeah, okay. So I didn't. So this 0.63 is not correct. So just average them. That's going to be the solution. Sorry, I initially had other numbers and then I changed them. Sorry. So it's going to be minus 1.3 divided by 3. So it's going to be 0.4333, right? So it should be minus 0.43 almost, right? Okay? So it was a mistake, sorry. Okay, everybody's clear? Okay, so if you got no question now, then this is pretty much time for introducing the idea of Gaussian maximum likelihood. So what is the idea of Gaussian maximum likelihood? It says like you have a data set, and this data set has lots of samples in it, okay? And what you want to do, you want to just model it with one distribution, and find out what is that distribution. So what you can do, you can think of one distribution, you leave the parameters of that distribution, theta, to be free, then you compute the likelihood, you maximize the likelihood, right? Now, one of the classical choices for that distribution is Gaussian. It's not coming at any surprise for you, right? Because many things in the nature you have is roughly normal, right? Like the height of people, the weight of the people, I don't know, education level of people, different things, they're usually normally distributed around something, right? And the key point in that case is only that you need to find the value of the mean, which is mu, and the variance, which is sigma squared, right? But this is correct when your data set collects scalars, right? If your data set collects vectors, what you're going to do? Then you need to think of a multivariate Gaussian distribution. So do you know this? Have you heard of it? Multivariate Gaussian. So this is multivariate Gaussian. So it's the same thing as the simple Gaussian that you had, but now instead of x being a real scalar, is now a vector. Yeah? Now, look at this guy for the moment. Don't panic, because we are not going to do like weird things with it. So, but one question here. So look at that guy, and then tell me what should be. So in this slides, you see that the dimension of x is d. Okay, so it means that x has d different entries. Now x is of dimension d. What should be the dimension of mu? What is it? X is of dimension d. What is the dimension of mu? It's again d, right? So it's the average of that vector x, right? So every single entry inside that vector, the expected value of it is the corresponding entry inside mu. So mu is also in R d, right? Now, look at that matrix sigma, which is the covariance matrix. What should be the dimension of this matrix? Yeah, go ahead. It should be d by d, right? Because you are multiplying x minus mu, which is a d-dimensional vector, to it from one side. So the number of rows should be d. And from the other side, you are multiplying x minus mu again. Again, it's d-dimensional, so the number of columns should be d as well. So sigma is again, the matrix sigma is again the covariance matrix, and this is d by d, right? Clear? And now sigma inverse is the inverse of that matrix, right? So inverse of a matrix is different. It's not, of course, 1 over the matrix. Definitely you know that, okay? But you are going to have, next tutorial, you are going to have an overview on linear algebra. Then you're going to feel more confident about these terms. But I think it's all okay for right now, okay? So you have that sigma, which is d by d. Those vectors are d-dimensional, so when you multiply everything, it's going to be a single number, right? The exponent. This is one thing. And also in the other term here, you have the determinant of that covariance matrix. Okay? And the determinant, you need to compute the determinant of the matrix again, okay? Which is the product of the eigenvalues, for instance, right? But again, not really important for now. Okay? But what does sigma mean? Sigma is pretty much proportional to the variance, but now in the multidimensional case. So when you look at that sigma, you have one diagonal of this matrix, which has d different terms. And each of them is the variance of the corresponding entry in the vector x, okay? And there are a bunch of other guys. They are somehow talking about how one entry is correlated to the other one, okay? If they are all 0, it means that they are all independent. But if they are not, this means that one and the other are dependent. Like if one of them is increasing, the other one is most likely increasing as well, and so on. Okay? But for the moment, you don't really need all of those details. So as I said, mu is the mean value. This is the covariance. So this is the definition of the covariance. You have the vector minus the mean value. So this is a vector of dimension d. This is again a vector of dimension d. You compute the outer product. It's going to be a matrix d by d. And then you compute the expectation. It's a huge thing, but you can do it. Okay? Now, more easily, you can think of a multivariate Gaussian distribution in this form. So say you have a bivariate 2 vector of dimension 2. What does it mean when they are, it is a Gaussian vector? It means that every single entry is Gaussian. but they are not necessarily having the same mean and the same variance, right? So if you think of this case, so you have x1 and x2, so this plane under is the space where your axis could change, the vector could change, and then your density function is going to be this three-dimensional function, and it's again a kind of three-dimensional bill. And where is this top? How you can find this top? What is the top of this bill? The peak of the hill? It is happening at where? If it was one-dimensional, where is the peak? The mean value. When it is multidimensional, it's the same thing. So where is the peak? It's the vector mu, right? So your vector mu has two different values, right? Two different entries. So if you put x1 to be the first entry, x2 to be the second entry, then you're going to hit that top. Clear? Right? And then the covariance matrix is going to tell you each of those reflections of this bill in the other plane, how wide they are, okay? Because they are the variance of every individual parameter. Clear? Yeah? Okay. So one thing that you can use to just have a bit of intuition about this multivariate case is when we plot the contour. Okay? So if you think of this bell, this three-dimensional bell, so it's a hill, right? A very symmetric, nice hill. Now, if I look at this hill, so anything on the ground is x1, x2, 1 point. So if I am here, for example, x1 is 1, x2 is 2, right? And I move another point, x1, x2 changes, right? And then I have one hill here, very symmetric. Now, if I cut this hill, what's going to happen? I'm going to see a circle, right? Now, if I do my cut at the top where it is very high density, yeah, the circle is small. The more I come down, the circle gets larger and larger, right? Yeah. Okay. Now, this is what you see here. These are the contours of that three-dimensional surface. So any circle in this contour, everything on it has the same density. Okay? And of course, when you get out of those contours, so towards the bigger contours, the density is reducing, right? Now what I'm going to do, I'm going to fix the height of my cut, okay? So I want to always see the same density, okay? I cut it. If I have this case where you can see my covariance matrix is simply the identity matrix, meaning that every single variable inside my Gaussian vector has the same variance 1, okay? And they are independent. Then you're going to see this circle. What's going to happen if instead of 1, 1 on the diagonal, I have 2, 2? What do you think about this circle? Does it get bigger or smaller? It's going to get bigger. Why? The variance is increasing, right? The bell is going to just get stretched, right? The heel is going to get stretched. You want to have the volume under the heel to be 1 always because it's a density function, so the top is going down, right? So this is what is going to happen if you go for higher variances, right? Same thing as the one-dimensional, right? But now the circle is getting bigger, right? So this is the circle where most of the times your vector is lying, the big one. Yeah? And that one is getting bigger because you have more variance, right? Your point could just vary more, right? What happens if I reduce that sigma, that diagonal? The circle is going to get smaller, right? So if I reduce it, then the bell is trying to squeeze itself so the top goes up and then the circle is getting smaller. Clear? Okay, so you see the circles because you assume x1 and x2, they have both same variances, right? But what if x1 has one variance, x2 has another variance? What's going to happen? Do you still see a circle as the cut? Ellipse, right? Because it is going to have variance in one direction more than the other one, right? So for instance, here I'm setting the variance of the first entry 2, the other one 1, right? And as you can see, x1 has more variance, so it's going to get stretched here, and it has less variance on x2, right? Clear? So it's not circle anymore, it's an ellipse, right? And you can increase that one. So if I just, instead of 2, make it 4, then it is getting to get stretched more and more. Right? And what's going to happen if instead of 0 on off diagonal, I put 1? What's going to happen? Can you guess it? I'm going to sleep good. Yeah? It rotates. Great. Okay. That's great. So I can sleep tonight very well. I feel like I've done a good job. So if I change that, then they are starting to get correlated, and then this ellipse is going to change a bit, rotate a bit, okay? But if you don't see it immediately, that's totally normal. Don't worry, okay? But the key point is that that sigma is somehow going to specify the shape of your contours, right? Clear? Okay. That's it about it. And now when we do multivariate Gaussian distribution, we simply think that our distribution is some multivariate Gaussian with some mean and some covariance matrix. And now, if I want to do estimation, or if I want to do the training, learning, what should I understand? What should I find? What are the unknowns that I need to specify? What are they? What do I assume it is normal with some mean and some covariance matrix. What should I specify to be able to write down everything? The mean and covariance matrix. Yeah? Clear what I'm talking about? So if I write down that distribution, if I don't know mu and covariance matrix, then whenever I put one xn here, I can compute this term. But this is going to be a function of mu and sigma, right? The mean vector and covariance matrix. And now it's a very large thing. I mean, lots of variables in it. But at the end, I can just play with them to find the optimal one, right? And what is the optimal one? Please? What is the optimal choice if we want to do what we have done all the day today? Yeah. The likelihood, exactly. So you are going for the data set. You put all of those data points inside this distribution, and for each of them you can compute the likelihood, or maybe the log of the likelihood. Then you have this function. So you have the log likelihood function, which is the function of mu and the matrix sigma. And then you try to find the vector mu and matrix sigma, which maximizes this likelihood function. Yeah.
Just a question on the previous slide.
Yeah. Here. Yes.
Do you expect us to know how the rotation functions as well?
No, I don't expect that. So I mean, once you get, like, after the next tutorial, probably you get a feeling about that. Because what you can see here is that here, for instance, the eigenvectors are that's 1, 0, 0, 1. So these are the eigenvectors. So your ellipse should be like this. But here, your eigenvectors are rotated, right? So the ellipse is going to get rotated as well. Yeah? And the value of this, diameters, these radiuses, okay? Each of them is proportional to the corresponding eigenvalue. Okay? But you're going to have one tutorial on Monday, and Mohammed is going to just go through this eigenvalue, eigenvector decomposition, things like that. Okay?
Okay.
Yeah. But I don't expect you to know it right now, because you don't need it, right? Obviously, for this lecture.
Yeah, I'm just wondering, because like before you can see intuitive where we stretch, but it's like
Yeah. Yeah, I didn't want you to know how exactly it rotates. The only thing was that I expected you to guess, like, it's going to rotate, right? Because the eigenvectors are not exactly like on the axes anymore. Okay, so now what we are going to just do the maximum likelihood, as I told you. So we have that distribution in mind. Mu and sigma are unknown, and then we want to specify that. We use our data set. We compute the likelihood of the data set. We find the parameters which maximize the likelihood. And this is the idea of the maximum likelihood estimation here with the Gaussian distribution. So you might wonder, as I said, why we're going to look at Gaussian distributions in classical cases. So there are a bunch of reasons. As I said, most of things coming from nature are supposed to be Gaussian. And the reason is simply the central limit theory, right? So what does it say? It says, like, if you have lots of random things adding up together, and they are happening independently, at the end of the day, as the superposed process that you see is roughly Gaussian, okay? This is why, for instance, we model the noise in the nature to be Gaussian, right? Because there are lots of resources for making that. They are all adding up, and then at the end of the day, we see something Gaussian, right? And for a lot of other things. This is one reason, but there is also another reason for that. The other reason is that many complicated distributions, you can write it down as the superposition of multiple Gaussians. Okay? So if I get one of those hills, I put it here, and I put another hill, I put it here, another hill here, pretty much I can make any landscape, right? So I need to just get lots of those hills and add them up. And then I can make even more complicated distributions. This is what we call it mixture of Gaussians. I'm going to mention it quickly today, but we're not playing around with that. But what you do with the Gaussian, you can then extend it to more complicated distribution by simply assuming multiple Gaussians. Okay? So these are the two main reasons that people are usually interested in the Gaussian distribution. So now if you want to do maximum likelihood Gaussian, there is nothing very surprising about this. So pretty much you are going to see what you expect to see. So let's take a look at this. So say I have this data set, I assume this Gaussian distribution, and then the whole task is to specify mu and the matrix sigma. So as I said, you can start writing down that likelihood. So what you see on the board, I mean that Sn, is when I put one of those xn's inside the multivariate Gaussian and I take the logarithm, okay? That is the term. This is what we had here. So this is Sn, you see, in the lower line. So if you take that one and you compute the logarithm, it's going to be the logarithm of the first coefficient, which is going to be those two terms. One of them has 2 pi, one of them has determinant, right? And the other thing that you see is basically the exponent, right? Because log of e to power anything is that thing, right? So, and then if you have multiple samples, you are going to compute it for every single of them, and then you add them up. This is going to be your log likelihood. This is what we had before. So this was the log likelihood. I have added this 1 over n here, but it's not important. I mean, you can keep it or you can drop it. So in the original thing when I did for you, I didn't put it, right? But it doesn't harm anything because it's a coefficient. If you maximize this guy, you maximize the log likelihood, right? Yeah? Okay, so this is going to be at the end of the day your function of mu and sigma is going to be a bit, I mean, at least it looks a bit complicated, okay? And I don't want to bother you with just opening up all the details, so I'm going to solve you a few sample cases, okay? The first sample case we can think of is when we do know that sigma is, for instance, identity matrix. So when the covariance matrix is identity, then what is the inverse of identity? What is 1 over 1? It's 1. Inverse of identity is identity itself, right? So if you put identity inside this term here, so this sigma squared is going to disappear, and then you're going to have inner product, so it's going to be simply norm. And then the determinant of identity matrix is 1 as well, so that logarithm is also going to vanish, okay? So at the end of the day, you end up with that term. And the only thing you want to find out is to just find out what is the optimal choice of mu. Clear? Covariance matrix is assumed to be identity, so the only thing I want to find is the optimal mean vector. Yeah? Now, what do you think? What guy is going to maximize this guy? Obviously, the guy who is minimizing its minus, right? correct? Yeah. And I don't need the first term because it's a constant, right? So what I want to just minimize that summation. I want to find a mu whose distance from all x's that I had is minimized. What is that mu? The central point, right? This is what we did in the clustering, correct? So if you go ahead, do the computation, you're going to see that this is exactly the average of x's that you have inside your data set. Does it make sense to you? Obviously. I mean, you have a bunch of vectors inside your data set. What is the mean value? Their average, right? You expect that happening, right? So one thing else that you can do, you can think of the more general case where you have a sigma. And now in this case, so it's going to be more complicated. I have given in the slides for you one particular case where, again, we get back to the one-dimensional scenario. Like the mean is just a number. The covariance matrix is, again, just the variance, just a number. And then I have solved it for you. I don't want to bother you. I initially thought I have a bit of more time, but I don't want to bother you with these details. Everything is inside this slide. You can go ahead and check what is the optimal choice of mu and sigma. And you're going to see at the end of the day, I mean, you just compute the derivative, you put it to be 0. You're going to see the optimal mean is, again, the average, no surprise. And the optimal variance is going to be the empirical variance you compute. Okay? So you compute your average on the data set, and then you get every single data point inside your data set. You subtract them from that mean, you square all of them, and then you average them as well. So this is the empirical variance you are computing. Okay? And it's, again, no surprise, right? Because you have a bunch of numbers. What is the optimal estimate you can do for the variance? Yeah? As long as you think this is a Gaussian distribution. Simply just do the empirical, compute the empirical variance, right? So maximum likelihood in these obvious scenarios is not giving you any weird answer. So this is exactly what is consistent with your intuition. And if you extend it to the more general case, like a vectorized case, multivariate case, your optimal choice of mu is going to be the average over your data set, and your optimal covariance matrix is going to be the empirical covariance matrix you compute over your data set, meaning that you get the average of your data set, then you start subtracting every vector from the mean, and then multiplying this subtract, this difference, to its self-transposed, right? And then you sum all of those matrices and then average them out. This is going to be the optimal choice of your covariance matrix. Okay? Again, no surprise, you have a bunch of data. This is the best you can do, and this is exactly what maximum likelihood is going to tell you. Okay? Any questions? Okay, so just as a hint here, so I do not expect, I mean, as I said, and one of your friends also mentioned, I do understand that you might have a bit of trouble with these vector functions and computing the gradient, things like that. No worries, I don't expect you to know it right now. When we get into gradient descent, we are going to do it together, okay? So it's just to give you the idea. I hope that the idea is now clear for you, okay? Now, that was the Gaussian thing. And now that I told you, I can show you, I want to just get back to the clustering problem, okay? So I want to get back to the clustering problem, which we did before, and now I want to just talk a bit more professional to you. So last week, you didn't know anything about this maximum likelihood, and the only thing I told you, I said, like, I have a bunch of data points, and I want to just cluster them, yeah? But now, you have a bit of more idea about what I'm doing. So what can I think? I told you I have clusters, right? I see I have clusters. So what does it mean? It means that I can think of multiple Gaussian, for instance, distributions, right? So you remember that example we had where we had two different clusters. So some guys are just lying here, yeah? And some guys are lying here, right? So what can I say? I can say anyone in this bag is either drawn from one Gaussian distribution. You see it, what I'm doing? Yeah? So one Gaussian distribution whose mean exactly is at the center of this cluster and whose variance is proportional to the size of the cluster that I'm showing you. Yeah. So everybody is inside this cluster is coming from one Gaussian distribution. So that is the distribution of those normal people. This is the distribution, again, a Gaussian distribution for the rich people, right? So their mean is here, their variance is something specific, right? So each cluster is, every point that I see inside my data set for one cluster is coming from one Gaussian distribution. And if I know the cluster of that point, then that is the Gaussian distribution is specified, right? So like I have this guy, and I can say like for that, say that blue circle is the cluster of cluster K. I can think every single point I have inside this cluster within my data set is coming from one Gaussian distribution whose mean is at the centroid of that cluster and whose variance is proportional to the space this cluster is covering. You feel fine with that? Do you see it? Do you see what I'm saying? This is a more, say, concrete way of modeling it, right? Because I could have the case that there is one guy from the other cluster, and it's suddenly, because of that particular random sampling, so that particular guy is just suddenly coming up to another cluster, right? So one Gaussian distribution, it goes forever, right? So with a very, very low probability, something in the other cluster could happen as well, right? But what do we mean by cluster? Most of the people are around this point and this point, right? And there could be one guy within the samples I have here, which is not really within the rich category. They are totally normal, right? The only thing is that in that particular month, they had to do one big payment. Yeah? That's the only thing, right? So this is now a bit more concrete way of modeling my data. And now I want to find the cluster. Okay? Or I want to find an algorithm which does the right clustering. And if I want to do that, given that I told you I am assuming Gaussian distribution for each cluster, how can I specify the mean and variance of those clusters? Using maximum likelihood, right? So I'm going to look at my data set. I try to come up with a maximum likelihood strategy which specifies the mean value of each cluster. Okay? Now, what I'm going to do now is that I assume that the variance of each cluster is 1, or the identity matrix in the multidimensional case. You might say it is not a good idea. You are totally right. I'm going to mention it quickly later. But this is what we did on, last week, implicitly, without you knowing that. Okay? And now, if I think of this, the only parameter remains here is basically that centroid of the cluster. Okay? Now, I am just going to quickly show you a few things we did last time. So, first thing, assume that I tell you that I have k different clusters. Okay? Each of them, I give you the centroid. So I say this is the centroid of the first one, this is the centroid of the second one, and so on. Okay? Then I tell you, look at this particular sample, xn, and tell me it's coming from which of those clusters. Assuming that each cluster is distributed Gaussian, what you're going to do? You're going to go ahead and compute the likelihood, right? So you're going to say that if it is from cluster 1, then I do know mu1, so I do know the PDF of that one. So I can put this value, this sample inside that PDF. I compute one parameter, right? One probability. And I compute it for the second cluster, and I do it till the last one. And I'm going to take the cluster whose corresponding probability is maximum, right? So this tells me that I am doing the maximum likelihood, right? So I'm taking the cluster which is most likely to be the cluster of my sample, right? So if you go ahead and do that, so you can write it down. Now the parameter that you want to find out is k, the index of the cluster. So I give you x, xn, and I want you to tell me what is its cluster. So you're going to say, okay, if it is from cluster 1, it's going to be a Gaussian with mean mu1. If it is from cluster 2, it's going to be a Gaussian with mean mu2, and so on, right? And you do know, I gave you all the centroids. So you do know all of those mu vectors, okay? So you're going to compute all of them for different k's. You have k different of them. This is a likelihood of k. You're going to take the index, which is maximizing this likelihood. Now, I'm not going to open it up for you this late, but if you go ahead and do that, you're going to see that basically you are going to take the cluster whose centroid is closer to your data point. And this is exactly what we did in k-means clustering, right? So when we wanted to assign a cluster to each point inside our data set, what did we do? We look at the data set. We just compare the distance to all centroids. We take the centroid which is very close, right? Clear? So what we did there was basically maximum likelihood. Now, one thing else, say that I do know the clusters. Okay? Say that I tell you that you have n different points. These points are coming from cluster 1. These points are coming from cluster 2. So on till the last cluster. Okay? Now, I want you to compute the centroid of these clusters, the mean value of these clusters. What you're going to do? It's again a Gaussian maximum likelihood, right? Because if you focus on only one cluster, you have all the samples within the cluster, right? And you do know that they are coming from a Gaussian distribution, right? And you want to estimate the mean value of this distribution. What is your estimate? It's going to be the average, right? Sorry, I do know. I totally understand you're very tired. So do I. I'm very sorry for that. But just not to get anything off the chart, okay? So what you're going to do is going to just focus on one particular cluster. So this is your data set now. And you look at all the samples that you have in that cluster. You try to find the mean value, which is maximizing the likelihood. And that mean value, as we did in a couple of slides multiple times, that is going to be the central point. Yeah? So if you do that, then the maximum or the choice of mean value, mu, which is maximizing the whole likelihood, is going to be the one which is the average of all of those points within the cluster. Okay? And this is what we did in the k-means clustering, right? So once we specify the cluster, the points within each cluster, then we go within that cluster, we just average the points, right? And this is the new mean, right? And then we repeat this, correct? So that step is again a maximum likelihood. So you are finding the centroid using maximum likelihood, assuming that your points are Gaussian distributed. Okay? And then the whole k-means clustering is a sort of iterative maximum likelihood. So once you assume that you do know centroids, you use maximum likelihood to just average to find the optimal choice of cluster. Once you do that, so it's going to be line 3. Once you do that, now you have the clusters. You're going to average those clusters to get the maximum likelihood of the mean value. Yeah? And then you keep on doing this till it converges. So k-means clustering basically is iterative maximum likelihood. Okay? But if I would have said this last week, no one would be here today, right? So hopefully you don't run away next week, right? Please. Okay? Sure? Okay. Cool. So that is maximum likelihood. The main reason I told you this, some people skip it. I didn't do that because when you get into machine learning, everybody starts talking like, okay, we want to estimate a model. We want to learn a model. What we're going to do? We're going to do maximum likelihood. And I know many people, they think that this maximum likelihood is something coming from Mars. Yeah? But it's not. It's what I told you today, exactly as easy as those Bernoulli variables. So if you know that, you're going to keep listening to the guy. If you don't know that, you're going to run away. You think you don't know it. So it's very important to know that what is maximum likelihood. But at the end of the day, all of those algorithms you know in unsupervised and supervised learning, most of them, you can interpret them as maximum likelihood, given some specific distribution you assume. Okay? So just a few notes. So one thing is that if you remember, okay, this is a very poor quality. But if you remember, I told you, I finally ended the last session with this particular example where k-means clustering was not working fine, right? Because it was not clustering really them into these left and right clusters. One of the reasons that you might find out right now is because k-means clustering is assuming the covariance matrix to be identity, right? So it's assuming that the clusters are always in the form of circle, right? If you don't want a circle, if you want an ellipse, what should you do? You should just estimate sigma as well, right? You don't assume sigma to be identity matrix. You can learn it as well, right? And if you do that, you're going to get into a better version of the k-means clustering. This is one thing that you can do. Another thing is the idea of mixture of Gaussians. So sometimes what you have is obviously not a Gaussian distribution, right? But what you can say I can write it down as the average of multiple Gaussian distributions, right? So I have multiple pi's. Each of them is getting multiplied to one Gaussian distribution. And each of those Gaussian distribution has different mean and covariance matrix. Now, if you superimpose all of these Gaussian distribution, you're going to get a very weird landscape. And if you keep the sum of pi's to be 1, this is still going to be a distribution. And then you can try to find out the maximum likelihood estimate of pi, mu, and sigma for every single n. If you do that, this is what you call it the mixture of Gaussian model. Okay? And this is going to get a bit more complicated. You need to use EM algorithm, expectation maximization. This is not a part of the course, but if you're interested, you can take a look at Bishop or McKay's book. Okay? So that's about this. So one last thing. This idea is what is making us nowadays generate data. For instance, generating images, right? So as I told you, random objects could be anything. Images could be random objects, right? A tensor of lots of pixels, all of them generated randomly. Now, what I can think in the imaginary world, I can think there exists one machine, right? And what is the property of this machine? Each time I press that machine, it's going to randomly generate one cat image for me, okay? Now, if I understand the distribution of this guy, yeah, it's over because I can push that button as much as I want and I get as much as I want cat images, right? Even cats who I have never seen, right? Correct? So this is the idea. So you have your data set, including all of the cat images, and then you would say, okay, I assume that there exists one distribution. I don't know what that is, but maybe I can model it with one distribution whose parameters theta are unknown, right? Mixture of Gaussians, for instance. I mean, obviously, it's not going to work for image generation, but think of that, right? A very complicated mixture of Gaussians, right? And then I get all of those data sets, try to find compute the likelihood, try to find the maximum likelihood, okay? Then I put my parameter theta to be that maximum likelihood. Hopefully, what I am finding is the true distribution of the data, the distribution of that machine I push, and I get cat image. And now I push it once, I sample from it. I get one image of cat. I mean, again, this is not high quality, but that guy is really generated by a generative model. And if you zoom in it, you see that it is not as accurate as a real cat yet, because your learning is still approximate, right? It's not perfect learning yet, okay? But it can generate one sample for you. This is exactly how everything works. LLM works exactly the same way. All of those diffusion stable models generating nowadays image for you do the same, okay? But of course, with a bit of more sophistication, okay? So this is what we are going to cover in summer for generative course, okay? But at the end of the day, the whole idea is maximum likelihood. You do maximum likelihood. So you try to find the best estimate, yeah? Given your super duper complicated model for the distribution, okay? So that's it for here. So as you can see, you can check Bishop first. This is the best suggestion. So I have given the details of what topics is in which chapter. And you can also take a look at McKay. I personally do like McKay, but I do give this honest opinion that Bishop has done a better job in that, given our lecture today. And you can take a look at the other books as well, but this is just for further read if you want. So that's it. So I'm going to take 5 minutes. I just was today on a super fast mode, so I really want to finish it as quick as possible. So I try to take just extra 5 minutes to finish this testing idea, and then we're good to go. Yeah? And you don't see me till the next Tuesday. Okay? So testing a model. Say I assume one model. Okay? I didn't know theta. I just assumed this to be something. I was like very good in computation, so I computed the maximum likelihood. Now everything is over, right? Now I know the distribution. Now the question that you might ask is that how you can make sure that what you have done is a good job, right? Because it could obviously fit the data that I have collected, but what is the chance that I sample from this and I get again a data that I want? What if I sample from it and it's not being exactly the cat image? Huh? How you can make sure? Because what you are doing is that you fit that distribution exactly to all the cat images that you have. But how you can guarantee that in future when I sample from this distribution, I still get a cat image. I need to test my model, right? So I need something to be able to explain whether my trained model is working fine or not. So one way that I can do is to just test it. So what it means that I go ahead and take a look at some new data, right? So I had some data in my data set. I did the maximum likelihood training. I got the distribution fine. Now I go ahead and collect some new data, okay? Some new images of cat, right? And then I need some metric, some number, right? So I get those samples. I put it inside my likelihood function, right? My likelihood function is no fix because the theta is no fix. I just found the theta star. I put it there. So if I get new samples and compute those probabilities, I'm going to have some numbers, right? If that number is high enough, meaning that it is close to what I got when I maximized the likelihood, then I would say, okay, I have done a good job because new samples are showing same probabilities as my models say, all right? So if I see that this guy, so this S that you see is the log likelihood, if I see the log likelihood that I'm computing now is approximately the one which I got when I was doing the training and I maximized it, then I would say that, okay, obviously what I have sampled is very likely to happen because I sampled and I got it, right? And when I put it inside my distribution, it's still saying that it's very likely. So my distribution is working fine, right? So this is when I would be confident that my model is generalizing, right? So if I get a new data, my model is still describing that new data, right? So here is good. But what if it's not happening? What if I do that and then a new data that I get, which I am taking from the natural process, right? The thing that I can sample or observe. And I put it inside my model, it says that it shouldn't be likely to happen, but it's happening. So what does it mean? It means that the model that I have trained with maximum likelihood is not working fine, right? So it's giving good likelihood for the samples I see inside my data set, but if you give me a new sample, it cannot work, yeah? So it's not generalizing, right? Now, in this case, you might wonder, okay, say this is happening, what can I do about that, right? So right now, we have not still developed the tools that we do now, enough that I give you lots of tricks that you can do. But one thing, which is the major thing we can do always, is to just do a bit of validation, okay? So what do I mean by validation? It means that when I want to just train my model, I did my data set, I collected my data set, I collect a bunch of extra data points as well, extra samples as well, and I call them the validation samples, okay? I keep them aside, I do not involve them in the training, right? So I use my collected samples, I do the training like maximum likelihood, I get my model trained, so I do have the parameters now. Now I'm going to check my validation value. So I'm going to go and use those validation samples, which I kept aside, I put it inside my model, I check the likelihood, okay? Now, what is the situation? It might be that this guy is significantly less than what I got when I was doing the training, right? If this is the case, then I should get back and modify the model that I had, okay? How do I modify it? For instance, I am going to modify some hyperparameters, and I'm going to give you an example, okay? If this is not the case, so if it is really doing fine, this is approximately the same one, then I say, okay, I tested it also on one validation set, and it was okay, right? Now, I can now give more confident out my model, and of course, anyone who wants to check whether this model is going to generalize or not is going to again find new set, a test set, which was neither validation nor training, and try to test it on that one as well to confirm my claim, right? But instead of talking about all of those blah blahs, let me just give you one example, the example of clustering. Yeah? So you are doing k-means clustering. So what is the hyperparameter? I mentioned it last time. The value of k, right? So the choice of the number of clusters is totally up to you, right? So you look at the data, you say, oh, it seems like 2 clusters are here, right? And you put k equal by 2. Now what you're going to do, you do perfect clustering on that, meaning that you get a very, very small risk, right, when you do the training. But next thing that you need to do, you're going in it, I mean, once you're over with the training, you are going to compute this risk, meaning that you just look at all the points inside your data set, find the distance to their centroid, you add them up. So this is your reference now. And now you're going to get a bunch of new validation data points, okay? Those validation data points, again, you go ahead and compute that risk for these validation data points, meaning that you cluster them using your algorithm, and then you check what is the distance of these new points from the centroids. If you see that the distortion or this risk is much larger than what you saw in training, what you can conclude? You can conclude that in training you do a very good job fitting your model to the data set, but when you get a new data set, sorry, it's not working. Yeah? Because your model was not good enough. Yeah? So what you can do, you can, for instance, increase k or reduce k, depending on where you are, right? And you get back again to line 1, and you try it. Again, you see very different validation result. You repeat it. You keep on going, till you see that the validation is approximately the same as the training. So now you would say, okay, this sounds to be a valid model, right? And now you give that clustering model out, and somebody else is going to collect a bunch of new data, again does the clustering, test it, to see whether what you have concluded after validation is correct or not, okay? So this is, don't worry, this is not what we do, how we talk about the hyperparameter tuning. I'm going to do it much more when we get into supervised learning, just to give you an idea how you can test the generalization of your model. So in practice, you usually don't do like collection of different things. Of course, you just have one data set, you're going to split it, right? Training, validation, test. Validation and test do not participate in the training. Test does not participate inside validation. So if you do that, it's cheating, because you are again somehow tuning your model for the data that you have. You should not do that. So that's it for today. If you wanted to know a bit more about this validation and generalization, you can take a look on these references, but we are going to talk about this more. So thanks a lot. See you next Tuesday. And by the way, I'm going to just release the first assignment tomorrow, okay?